In this video, we continue our discussion of reactions that conjugated dienes undergo, here focusing on the so-called Diels Alder reaction. This particular reaction was named after the German scientists Diels and Alder, who developed this reaction. They won the Nobel Prize in Chemistry in 1950 for this reaction due to its importance. In particular, what is amazing about this reaction is the fact that it creates two new carbon-carbon bonds within a single reaction. And carbon-carbon bonds in general are notoriously difficult to create. If you think back about all the different reactions that we've learned about so far in Organic 1, as well as Organic 2, very few of those create new carbon-carbon bonds. And the reactions that do create new carbon-carbon bonds generally only create one carbon-carbon bond per reaction. This reaction yields two new carbon-carbon bonds within a single reaction by taking a conjugated diene, reacting it with an alkene, to ultimately create a ring, such as we've shown here, that is formed by creating two new carbon-carbon bonds, which are highlighted in pink on the product side. What we are going to focus this video on is looking at the reaction mechanism for the Diels Alder reaction to enable us to predict the products of these reactions. We will also look at characteristics of the R groups on the alkene, R and R prime here in our schematic, that enable this reaction to effectively take place, comparing and contrasting some different types of R groups to evaluate whether those R groups will make the reaction take place really well or make the reaction take place not quite so ideally. So that's what we're going to be doing in this video as we focus on our Diels Alder reaction. As we begin digging into this, I want you to be aware of some key terminology. Specifically, in this Diels Alder reaction, the alkene is also known as the dienophile when we are working with a Diels Alder reaction. So in other words, when we are discussing Diels Alder reactions, what we are describing is the reaction of a diene with a dienophile. Phile means love, so the alkene, what we're saying is it loves dienes. In other words, it really desires to react with dienes. So we will describe the alkene and the dienophile synonymously throughout this video, so get accustomed to seeing the word dienophile and reading that as alkene. So we will be reacting our conjugated diene with a dienophile here. To understand how we create two new carbon-carbon bonds and a ring within the single reaction called the Diels Alder reaction, we're going to look at this example of our diene starting material, and that will always be a conjugated diene. If it's not a conjugated diene, this reaction is not going to work. It's entirely reliant upon this continuous sp2 system that we see within a diene. Now, there could be additional substituents out here, but the core of the molecule needs to absolutely have that conjugated diene functional group present. We'll always be reacting with the alkene, which we refer to as the dienophile in this particular reaction. Now, in the reaction known as Diels Alder, it is a one-step mechanism where within one reaction step, we are going to create the two new carbon-carbon bonds and the ring in one concerted mechanism. To illustrate this, the best approach is to line up the structures so that it is evident where the new bonds are being formed to make the ring, including those two new carbon-carbon bonds. In order to accomplish that, what I recommend first is to rotate the carbon-carbon single bond to create a so-called S-cis diene. When we say S, what we're referring to by the letter S there is single bond. So a carbon-carbon single bond is what we are rotating around to enable the two alkene groups to be cis to one another. So in our structure above, our two alkene groups are here and here. Right now we would describe those as being trans because one's going up relative to the carbon it's bonded to, the other is going down relative to the carbon it's bonded to. Connecting those two alkene groups is this carbon-carbon single bond. And within carbon-carbon single bonds, when they're part of a chain, there can be free rotation around that carbon-carbon bond. And so what we do is rotate around this bond in order to place those two alkene groups cis to one another. And the purpose of this from the perspective of writing out the mechanism is that by placing those two groups cis to one another, we're going to be able to more easily visualize the electron flow that has to go on in order for this reaction to take place. And in actuality, when we are doing Diels-Alder reactions in the real world with various different molecules, it is essential that the diene be able to assume this S-cis conformation in order for the reaction to take place. So we just freely rotate around that carbon-carbon single bond within this chain to take those two alkene groups and make them cis to one another like so. So we still have a 4-carbon chain, just like we did up top. We've just rotated around that carbon-carbon single bond in order to make those two groups cis to one another. We will then react with our dienophile, which I'm going to orient the dienophile such that the alkene group is vertical. This will help us in visualizing where the electrons are located. I'm going to go ahead and put my R prime group and my R group on there. And now we are set up with the two molecules, the diene on the left and the dienophile on the right, correctly aligned in order to carry out the mechanism. So whenever I'm drawing a Diels-Alder mechanism, I always rotate around the carbon-carbon single bond of the diene so that the two groups, the two alkene groups, are cis to one another. And I also orient this so that it's oriented kind of in this vertical way so that the end points of the diene, that would be here and here, that's the end, the terminals of the diene group, are oriented at the very top and the very bottom facing the dienophile. So you want the ends of the diene group here and here facing the dienophile, because what's going to happen during this mechanism is that the pi bond from our dienophile, from one end of our diene rather, not dienophile, this is the diene, the pi bond from one end of the diene will start down here. You could have started up here as well. It doesn't matter at this point. So the diene pi bond is going to come over and attack the carbon, one of the two carbons, of the alkene group of our dienophile. Now, when that happens, we would go over the octet rule at this carbon unless we do something else. Pi bonds, we've seen in a variety of situations, are relatively reactive. They are able to migrate about. And so what we do to avoid going over the octet rule is we take this pi bond and it comes off here. It's looking for something to form a bond to, and what it forms a bond to is the other end of the diene group. So we take the pi bond from here, it comes over, forms a bond to the other end of that conjugated diene system. So one end of the conjugated diene system comes over to attack the dienophile to get things started. That forces these pi electrons from the dienophile to go somewhere. They come and latch on to the other end of the diene group. And then what that forces is these pi electrons right here have to go somewhere because we can't go over the octet at this carbon on the end. And where they are going to go is they're just going to come over one spot to right here. And that is perfect because that is going to enable the carbon atom right here, which had lost its octet as these electrons came away, to regain its octet. And so as a result of this series of just 3 electron pushing arrows all going in the same direction, notice how they're all going in this counterclockwise orientation. We could have also drawn them all going clockwise, starting here, coming over to here. This goes clockwise to here. This comes clockwise to here. In that concerted manner of all of these arrows working together, we are going to, in effect, create 2 new carbon-carbon bonds. That's going to be a carbon bond between here and here, as shown by our blue electron pushing arrow there on bottom. We're going to create a new carbon-carbon bond between here and here, so the other carbon of the dienophile connecting to the other end of the diene. And then finally, this pi bond right here is going to come over to make a double bond right here. So we can map out the product of this reaction, and I'm going to highlight the diene-derived portions of the molecule in pink, and the dienophile-derived portions of the molecule in green, so we can clearly visualize where all of the groups came from. So I'm sketching out, following the pattern that we did at the left here, where in pink highlight, I'm putting the atoms that originated from the diene. like so. I'm even keeping the orientation the same. That's why I rotated everything around initially so that I could show it in the same orientation in the product really clearly. So we've got our 4 atoms here, 4 atoms here. Our double bond needs to go right here. I'm putting that in red on the product side. That corresponds to the pi bond that was right here on the reactant side. We took that pi bond, we moved it down to here, so that's where we get the pi bond at for this. And then we have connections via the blue electron pushing arrows over to the dienophile from here and here. So I'm showing those new bonds here and here in blue. And the 2 atoms are linked here, the 2 atoms of the alkene. So I'm going to go ahead and draw those in black, and I'll highlight over it in green to keep my color coding consistent. The carbon from the dienophile that was on top is bonded to the R prime group. The one that was down below is bonded to the R group, so I plug those 2 in here. And I will also go ahead and, just to be consistent, highlight those in green as well. So what we're seeing is that we have linked the diene to the dienophile using this set of 3 electron pushing arrows that are all going simultaneously. So we're making the new covalent bond in blue right here. At the same time, the pi bond from the dienophile comes over to make the bond right here, and the pi electrons that are shown in red come from here down to give this. So in effect, what we are always creating is a molecule that has 2 new carbon-carbon bonds plus 1 new ring. That will always be the case no matter what reactants you are using, is that relative to what you started with, you will always have 1 additional ring and 2 additional carbon-carbon bonds within the product of your Diels Alder reaction mechanism. Now we can dig more deeply into this reaction and this mechanism by considering what factors about the dienophile will make the reaction more or less favorable. With respect to the dienophile, factors that will make the dienophile more reactive are having R group or R groups that are electron withdrawing. And so the more electron withdrawing the R groups are, here or here, the more strongly the attraction will be between the diene pi electrons and this carbon of our alkene. Because if the R group here is electron withdrawing, that's going to make this carbon more positively polarized, and hence the electrons will be more drawn toward it. And so I'm going to go ahead and write that down, that as a rule here, when we're thinking about what will make a Diels Alder reaction favorable, the rule is that electron deficient alkene groups react best in Diels Alder. And when we say electron deficient alkenes, we're referring to electron deficient dienophiles. So in other words, if R and or R prime are electron withdrawing, the reaction will be more favorable. On the other hand, if R and R prime are electron donating, such as by having alkyl groups there, the reaction will be less favorable than if instead there were electron withdrawing groups there. So when we are looking in the context of this reaction, we're thinking about electron donating versus electron withdrawing groups. What will act as an electron donating or an electron withdrawing group? We need to think about that a bit in the context of what's going on in this reaction. So let's consider some examples of electron donating versus electron withdrawing R groups that can exist on the dienophile. I've redrawn our dienophile here, our alkene that has the R groups. So we're thinking of what's the structure of those R groups. I'm going to discuss a list of groups that are withdrawing, meaning groups that will make the reaction with the Diels Alder be more favorable. And I'm also going to include donating groups. Donating groups will disfavor reaction at that particular alkene carbon. So electron withdrawing groups favor the reaction, making the Diels Alder reaction go well at that particular alkene carbon. Electron donating groups disfavor the reaction. So in the realm of electron withdrawing groups, a very common theme for strong electron withdrawing groups is that they will have a carbonyl group directly connected to the alkene. So I'm just going to put carbonyl and then R double prime here just so I'm not duplicating any of the other R groups that we have here. So a variety of situations where we have a carbonyl and then whatever other group we want there. Some specific examples would be having an aldehyde group present, a carboxylic acid group present, COOH, having a ketone present, carbonyl group directly bonded to an alkyl group, which I'll abbreviate just as R, and I'm going to put a line here with a squiggly at the end to indicate that's where it connects to the rest of the molecule in all of these situations. So there's a variety of different possibilities here. You could also think about an ester, that is carbonyl bonded to oxygen, bonded to an alkyl group. So a huge variety of different possibilities there. And what's going to be true in all of those that makes them electron withdrawing is that if we take a look at the structure of a carbonyl group, and I'll just put carbonyl with an R group here, and we link that to our alkene. So we come over here and we plug in our alkene, and then I'll just put R prime out here. So what I've done is I've taken this generic dienophile and I have gone ahead and put the electron withdrawing group right here. The ways that we can illustrate this group is electron withdrawing is groups will be electron withdrawing if they're pulling electron density away from the alkene and toward themselves. There are two ways that this group pulls electron density away from the rest of the molecule and toward itself. Number one, first and foremost, the most important factor in evaluating whether a group is electron withdrawing or electron donating is resonance. Resonance is more important than induction in determining generally the behaviors of groups. And so by resonance, what we could show is a second resonance structure where the electron density is being pulled away from the alkene, coming up to here, and the pi bond from there goes on to the oxygen. So there's a second resonance structure that will illustrate that the electron density can be shown shifted toward the electron withdrawing group. So we can illustrate as this minor but important resonance structure that the pi electrons come up to here from our alkene pi bond. When that happens, the electrons from the pi bond of the carbonyl have to go up onto the oxygen, so that puts a negative charge on the oxygen, positive formal charge over here, and the take-home message is that this group of having a carbonyl directly adjacent to the alkene group is electron withdrawing because we can show this second resonance structure indicating a shift of electron density toward that electron withdrawing group. By definition, electron withdrawing groups are pulling electron density toward themselves and away from the rest of the molecule. So this group that we have circled in blue here is electron withdrawing by resonance. It is also electron withdrawing by induction due to the fact that there is that electronegative oxygen atom present here that will be, by virtue of its high electronegativity, be pulling electron density toward itself. So this group is electron withdrawing for the primary reason of resonance, that it's moving electron density toward itself and away from the rest of the molecule when we draw the second resonance structure for it. And secondly, via induction, because the electronegative oxygen atom is pulling electron density toward itself by that long-range bond polarization. So that's one example of an electron withdrawing group, and we can highlight why it's electron withdrawing by using that argument of resonance. Similarly, we can also look at the electron withdrawing capabilities of some other common groups that we may see linked to our alkene of the dienophile. For example, if we look at a nitrile group, that's a carbon triple bonded to a nitrogen, so like so. And this group, our nitrile group, is electron withdrawing for the same reasons as our carbonyl group. That is, by resonance and induction. And we can illustrate the reason it's electron withdrawing by resonance using the same sort of arguments that we did for our carbonyl group, in that if we place the nitrile group in that R position of our dienophile, so we place the nitrile group right here, we can show there is a second resonance structure that would correspond to pulling electron density away from the alkene group and toward the nitrile group by taking the pi electrons of the carbon-carbon double bond, moving them up to here, and simultaneously taking the electrons from that carbon-nitrogen triple bond and moving one of those pi bonds over onto the nitrogen. We make a second resonance structure here where the negative charge is now on the nitrogen. And like so, we have our positive charge right here on this carbon. And what we are seeing is the illustration that the nitrile group is electron withdrawing by resonance, because by resonance we're pulling electron density and moving it away from the starting structure and toward the nitrogen. Likewise, there's also some induction going on there, although nitrogen is not as electronegative as oxygen, and so there's not quite as much of the induction electron withdrawing effect going on for the nitrile group as there is in the case of the carbonyl group. But in both cases, both groups are strongly electron withdrawing, with the main factor that leads to that electron withdrawing effect being resonance. Resonance is generally more important than induction in determining the behavior of systems. Now, what if we bring in another type of group? What if we bring in a nitro group, NO2? What would that be classified as? Is it going to be classified as electron withdrawing or electron donating? So drawing out the Lewis structure of an NO2 group, a nitro group, NO2, there are a variety of different possible resonance structures for this. This is the most stable of the resonance structures, so this is our NO2 group right here. This group is electron withdrawing as well by arguments of both the resonance and the induction, just like our other situations up top where we had a nitrile group or a carbonyl group present. And the reason is that we could take the pi electrons, move those over to make a carbon-nitrogen double bond while moving one of the pi bonds from the nitrogen-oxygen bond out onto the oxygen. In addition to that resonance argument that makes the nitro group strongly electron withdrawing, there are also not one, not two, but three electron withdrawing by induction atoms here. That is, the two oxygens and the nitrogen are both more electronegative than carbon, and they're going to be pulling electron density toward themselves by induction as well. But as we've said before, resonance is the more important factor, and certainly the nitro group has resonance we can use to illustrate that the electrons are being pulled away from the alkene group of the dienophile and being pulled onto or toward the nitrogen and oxygen atoms. So that makes these groups all electron withdrawing and makes the reaction of the alkene dienophile with the diene more favorable. On the other hand, groups that are electron donating are going to make the reaction less favorable. What do we mean when we think of groups that are electron donating? Well, classically, a group that we have recognized previously as being electron donating by induction are all sorts of alkyl groups. So if we have just a carbon chain there of anywhere between one carbon, meaning a methyl group, or 1,000 carbons, however many you want, if it's an alkyl group, it's going to be electron donating by induction. There's no opportunity to draw a resonance structure showing that electrons are being donated toward the alkene group. Instead, it's just a matter of bond polarization there and the fact that alkyl groups are electron donating. Now, here's a scenario that may cause you to scratch your head a little bit. If we have an O alkyl group, where R here can be an alkyl group, it could also be a hydrogen, it could be a variety of other atoms there as well. That is going to be an electron donating group. So why is that an electron donating group? Well, let's draw it in as our R group and try to illustrate that. So if we have our dienophile, plugging in a generic R prime group down here, I'm going to fill in my R group up top here with O alkyl. So I'm just going to do OH here. we could put in whatever we want there. The key is just that there's an oxygen here on the adjacent to the alkene group. So you have alkene and then an oxygen directly bonded there. What's going to be the case there is that by resonance, this group of having an oxygen adjacent is actually electron donating. Here's how. So the lone pair electrons come down to make a carbon-oxygen double bond, and the pi bond electrons come on to the carbon there that they're connected to. And so we can draw a second resonance structure here that will show what has happened here. So we'd have a carb anion, pi bond there, OH group. We would end up with a positive charge on the oxygen here. But this, although a less prevalent resonance structure than the starting structure we started with here, nonetheless illustrates that the oxygen can, by resonance, donate electrons toward the pi bond of the alkene, and hence that makes this group electron donating rather than electron withdrawing, because even though the oxygen by induction would be withdrawing electrons, pulling electrons toward itself and away from the rest of the molecule, resonance is more important. And by resonance, the electrons are starting off here on the oxygen, and they're ending up going toward the alkene group to make this resonance structure. So that means that the net effect is that the oxygen atom here, in this context, is electron donating, because we can take that lone pair electrons and move them over, donating them by resonance. So therefore, the net effect is that when you have an oxygen directly connected to the alkene group, it makes that group electron donating in that context. So this also holds true not only in the case of just an O-alkyl group, but also in the case of, depending upon the structure of the ester, if the ester is set up so that the oxygen atom is directly connected to the alkene, and then we have the carbonyl, that creates a group that is electron donating as well, because you have an oxygen here, sp3 oxygen, directly connected to the alkene group, and so those lone pair electrons can behave just like they did with the O-alkyl group, where the lone pair electrons can come over to create another resonance structure that illustrates the electrons moving toward the pi bond, and hence an electron donating situation. And so the general thing to look for, or the general rule here, is that groups will be electron donating by induction, by resonance, if they have a lone pair of electrons on that first atom of the R group. So groups will be electron donating by resonance if there's lone pairs adjacent to the alkene. So if we look at that first atom away from the alkene, the first atom of the R group here, if that has lone pairs, those lone pairs are going to be able to come over by resonance to act as electron donors, as we showed with the O-alkyl group when we drew out the second resonance structure for that and showed how the electrons from the lone pair could move over to make a carbon-oxygen double bond. So due to the fact that resonance is the most important factor in determining whether a group is electron withdrawing or electron donating, that means that although these oxygens are definitely electronegative and by induction would be electron withdrawing, by resonance they are donating electrons, and resonance is more important, and so therefore the net effect is that those groups are electron donating and they're going to make the reaction less favorable. Now, in the next video, what we will do are some additional example problems of Diels-Alder reactions where we will use structures that have various R groups on the dieno file, and we will use this information we've learned here to predict what the major organic product of the reaction would be and what the mechanism would be that leads to that reaction, that leads to that product.